So, I was discussing about the another spectroscopy, that is as I told ESR, electron spin resonance spectroscopy. Okay. And NMR, nuclear magnetic resonance spectroscopy. Okay. So, here this electron half spin that we are quite familiar, we have discussed, and considering this electron spin only we are able to explain the fine structure. And for explaining the hyperfine structure, one has to consider the nuclear spin. Nucleus is having proton and neutron. Proton also have spin half, neutron also have spin half. Okay. Similar to electron have the spin half. Okay. So, now this interaction with the magnetic field, it is because of the magnetic moment of the electron or magnetic moment of the nucleus. Okay. So, if you have a multi electron system, and then what will be the magnetic moment of this multi electron system? So, there we find out the resultant total, not total, resultant spin of the multi electron system. So, we use the vector model. Similarly, that similar vector model one can use for also this nuclear spin. Okay. Same way one can use. So, just following the similarity for this just electron spin, whatever the way we have considered. So, for nuclear spin also one can consider same way. Okay. So, just so in case of, if you have a nuclear spin of an atom, if it has multi electron, so total spin is S. Okay. So, spin S is not half. The total spin, it will depend on how many electrons are there. So, S1, S2, S3, they have individual spin. So, all may be half. So, now using the vector model one can find out the resultant S. Okay. If that is the electron spin, if S is the electron spin, so magnetic moment mu, you remember. Okay. You remember, so that is a Q in general, let me write Q by 2m. Okay. Then I have to write S H cross. So, 8 in quantum mechanics. So, S, it basically this spin momentum is square root of S S plus 1. So, we have earlier an H cross. Okay. Earlier we just use S H cross, but actually one should write square root of S S plus 1. Okay. So, this is for, they say, for a electron, for a system, a multi electron system of this. Okay. So, there one can find out so this way, if it is for one electron, then I think for one electron. So, then this we can just write generally S is a Q it is the minus E for electron, Q minus E for electron divided by 2m, and then here I can write E minus E H cross, and then this one S plus 1. Okay. And this is written generally, this one we write mu v, and square root of, and we write g here on g we write, and then square root of s plus 1. Okay. Earlier we just wrote s, so actually if s is half, so g is 2, so it is a mu v for 1 electron. S if you consider half, then it is for 1 electron. If S is more, so that is a for, so so this called Bohr magneton. Bohr magneton is very important for electron mu v equal to E H cross by 2m. Okay. Similarly, if we consider this if I so I will write mu s for spin. If this now mu n, if I write mu n, nuclear have spin. So following the similarity, I can write mu n equal to g. Okay, g. Here I will write mu n, nuclear magnetic moment. I think I did mistake. Mu n, here generally people write this Bohr magneton. Here I think we write beta n. Okay, beta n, and then here if nuclear spin, because proton have half, neutron have half, so these are nuclear spin we tell, because both are having the same. So how many neutron and proton are there? So together using the vectorial model, one can find out the resultant nuclear spin. Okay. So it can be only for proton, it can be only for neutron, or it can be for together proton and neutron, but since all are similar in terms of spin, so because both are having half, so that is why, and mass also both are having more or less same mass. So that is why so we tell nuclear spin, not proton spin and neutron spin separately, both are same in terms of spin half and in terms of mass. So these are nuclear spin. So nuclear spin generally here, nuclear spin whatever here electron spin s we use for nuclear spin, we use I. Okay, notation I. So I is basically, so one can write this way. Okay, nuclear spin for nuclear. So this nuclear magnetic moment, spin magnetic moment, that is in terms of Bohr magneton one can express. So here in terms of what is called some nuclear some special name, it is still exactly I didn't remember. Anyway, so it has, what is this beta n? It is similar to mu b, Bohr magneton. It is similar to Bohr magneton. It is not Bohr magneton, but beta n, from this similarity, beta n is basically E H cross. So this charge, so generally that is why people generally it is just use Q, charge of nucleus. So here then 2 m. Okay, what is 2 m? M is, what is m? M is the mass of the proton or neutron. Okay, mass of the proton or neutron. Okay, so this the nuclear magneton, Bohr magneton, these are for, yeah, I think this nuclear magneton is called nuclear magneton. So this from similarity it is tell we tell. So, this value is different. See this now here this question is this we neglect this nuclear effect most of the time. Why? Only magnetic moment due to the electron we considered, but magnetic moment due to the nucleons we neglect, but it has effect, it is minor effect, very fine effect. Okay. So, that is reason is that just from here you can see. So, you see this it depends on mass. So, mass of electron and mass of proton. So, you see it is what is the difference is I think this is 10 to the power mass of this electron is 10 to the minus 27 and this is 10 to the minus 24. Okay. So, it is order of I think 1000 order of 3 magnitude vary. So, that is why this magnetron is its value 9 it's I think what is the value of Bohr magnetron? I think this the yes. So, it is minus 27 and then other one is yes, I have to check it. What is the value that I have written somewhere or it is not there. Well, so it is 9.27 into 10 to the power 20. Okay. So, it is 9.27 into 10 to the power minus 27 Joule Tesla inverse. Okay. Whereas this one its value is 5.05 into 10 to the power minus this is 27 and this other one is I think 24. Yes, that is right. This is 24 10 to the power 24 and this is 10 to the 27. Okay. So, you see this here 10 to the power minus 24 and here 10 to the minus 27, there is 3 orders of magnitude difference. Okay. So, magnetic moment of a nucleon and magnetic moment of a electron. So, this difference is a 3 order of magnitude the difference are there. Okay. So, these are smaller than this other one, that is because of the mass of the proton or neutron, and that is why this is a very weak magnetic moment of nucleons, and thus this we most of the time we neglect the nuclear effect on the atomic spectra, but it is there, although it is fine, but it is there. And there are many cases. So, this effect is one can see this effect and one can analyze the system using some spectroscopy, because as I told this considering electron spin, that is fine structure, effect is small, and considering the electron spin it is the hyperfine structure, even effect is this splitting etc. These are even very small. Now, fine structure and alpha this hyperfine structure, that change energy level change it's very small. Now, now that effect is seen in the atomic spectra, but how to it's you need again to see this one, again you need very high resolution of the spectrometer, and that is what people used to do, but it is again it is difficult to resolve this fine structure and hyperfine structure. To resolve this hyperfine structure, it is really very difficult. So, to overcome this crisis, this spectroscopy, resonance spectroscopy, is very popular, very useful, because resonance phenomena, you see, this is very strong, and one can use the resonance to probe this kind of finer splitting of the energy levels. Okay. So, that is why that is the reason why these two spectroscopy are very popular to see this kind of tiny change of the tiny effect of the on the spectral lines. So, here directly one can find out this this separation of this. So, here, so this spectroscopy in which range, that easily you can see, or I can tell you. So, what yes. So, now in both cases one has to apply magnetic field. If you apply magnetic field, what happens? So, there will be change of energy, interaction ratio, that is mu dot B, that is the energy, right, mu dot B. So, this energy mu dot B, that is the energy due to magnetic field, due to interaction of magnetic field with the magnetic moment, okay, magnetic moment due to the spin or due to the neutron or both together. Okay. So, if you have nuclear spin as well as electron spin, so S and I, now what will be the resultant spin? So, the resultant spin generally we write F equal to just simply S plus I, just vector addition, okay, as similar as J equal to L plus S. So, the way resultant total angular moment we find J, similar way here this total spin angular moment one can find out that S plus I. So, that F will be this. So, it is similar to J. Okay. In same way one can find the total spin magnetic moment of the atom. Okay. So, this mu dot B and this, if you apply this along the z direction, this one along the z direction, okay. So, and then this one mu is so it is the J, G, okay. In case of electron it is mu B, okay, G mu V, and S Z I can write, okay. Actually this is S Z. So, this we write M or MS, and then your magnetic field along the Z direction. If magnetic field along the Z direction, one can write BZ also. So, this is SZ, this is we are writing M. Okay. So, let me write SZ. Okay. Now, this energy mu B, that value you know, for electron, G you know 2. Okay. If for one electron this is half, and now you can find out this value, this this value in the range of this will be I think say some value into 10 to the power 6, just I think I have to see. Okay. And this if you take this just divide by h, okay, then it will be nu divide by h divide by h divide by h, and you put all this value. So, this it will be then frequency, and that frequency comes, this frequency comes 100 into 10 to the power 6 hertz if this magnetic field if this magnetic field Bz, it is 2 point exactly. So, you have to put this value 2.3487 Tesla. Okay. So, 2.34 or 2.35 Tesla if you apply magnetic field, okay, then what will happen? Then this will be the change, there will be the magnetic interaction. So, you remember, so if I have before applying magnetic field, this is the, so this if I apply magnetic field, okay, so this will be splitted into 2 because of Sz, okay, plus half and minus half. So, before applying magnetic field it was degenerate. Now, this is, it will be splitted into 2 lines. Okay. So, this for plus half and minus half, right. So, for spin up electron and for spin down electron, okay, this will be separation. So, and this splitting because of this magnetic field, if we apply magnetic field. So, due to electron spin, it is there, magnetic moment also it is there. So, if there is no magnetic field, so the states are degenerate, it will have the same energy. Now, if we apply the magnetic field, of this amount 2.35, so this splitting, it will be splitted, and it will be splitted by, in terms of energy one can write, but I have written in terms of frequency. So, this energy difference and corresponding frequency is 100 megahertz. Okay. So, this splitting will be in megahertz range. Okay. So, this is basically its radio frequency, this range is radio frequency range. Okay. This will be the radio frequency range. Now, I did one mistake. I think, yes, this whatever I am showing, I think this I have done mistake. This it should be this, for this it is calculation I have done for, okay. For electron it is, I did mistake. For electron it will be just whatever here I have shown you, this here I have shown you, it's for just, I think I will write beta n, and other is same. Okay. Other is same. So, then if we apply this magnetic field, then nuclear spin, this before applying magnetic field, whatever the for nuclear, that they are degenerate states. Now, after applying magnetic field, this will be splitted into 2 for plus half or minus half, if one nucleon is there, like just you consider for silicon. For other, you see this, if just two splitted into 2 lines that I have considered, but if that I, if it is not half, if it is 1 or if it is 2 or it is 3 by 2 etc. So, it will be split into both. So, for simple cases just we have considered spin half, okay, spin half, nuclear spin half. Okay. So, then it is split into this, and then we will get splitting, and that splitting is in terms of frequency, that is, and that is 100 megahertz. Okay. It is basically radio frequency. Now, I have system, if I apply magnetic field, then I am getting splitting of the lines this, okay, fine. Similarly, if I consider this electron spin mu b electron spin, then this value will come, it comes around 9, yes, that, okay. So, this value I will get, this value I will get, this value I will get 9500 into 10 to the power 6. So, this we kept same in megahertz, and so that is just applying very small field. This is 0.34 Tesla. Okay. So, in case of electron spin, okay, so it was degenerate state. Now, if we apply magnetic field of this 0.34, this very small field, then it will be splitted, and that splitting in terms of frequency, that is in megahertz range. It's now you can see this, earlier it was 100, now it is 10,000. Okay. So, 1000 more. So, it will be in radio frequency, then microwave range, it will be in microwave range. Okay. So, in case of, so just in case of electron spin, applying magnetic field, I can split the energy levels. That splitting purely because of electron spin, and this splitting, it is in terms of frequency, it is in the range of microwave frequency. And in case of nuclear spin, if we apply magnetic field, you have to apply magnetic field 2.35 Tesla, then this splitting due to nuclear magnetic moment, okay, or due to nuclear spin. So, the splitting will be 100 megahertz, since it is in radio frequency range. Okay. So, now point is that to sense the energy levels, splitting of the energy levels, okay, due to the electron spin or the nuclear spin. So, one has to nuclear spin. Okay. So, that applying magnetic field, that I can separate them, effect of nuclear spin, effect of electron spin, I can split them, applying magnetic field. How much splitting I want to do, so that I can control using the magnetic field. Okay. Now, applying magnetic field, it is splitted, both are same way one can see. Okay. The splitting due to nuclear or just only it is magnetic field. For nuclear spin, you need to apply higher magnetic field. For electron spin, you need lower magnetic field, but splitting are in microwave range in one case, and another case it is in radio frequency. Now, you see, now external in this spectroscopy, now ESR and this NMR, these both are based on this concept. Now, in case of NMR, now to make resonance, okay. So, something externally I am putting here, that is basically I am putting the radiation on it of this radio frequency, radiation if I put on it. So, it will resonate. So, if when frequency will match with this separation of these energy levels, okay, then there will be resonance, and that resonance we detect, okay, because resonance is a strong, very strong phenomena. So, only now one has to be variable, either incident radiation is fixed, okay, or incident, yes, or then we can vary the magnetic field to get resonance, to get the frequency in the same range, same for this, okay. So, either varying the magnetic field, also two externally I can control using the two parameter, one is magnetic field, another is incident radiation or incident electrical signal, okay. Yeah, better to tell radiation of frequency, microwave frequency or radio frequency. So, one is called ESR spectroscopy. So, in that case we use the microwave radiation, okay, or microwave frequency, externally signal we put on it, and either we can vary the frequency of the signal or radiation of the incident signal or radiation, keeping the magnetic field fixed, okay, or other way one can do, putting this radiation of particular frequency, microwave radiation, we can just change the magnetic field. So, this frequency or separation will change. So, when these two h nu of this h nu will be equal to this energy E, magnetic interaction energy. So, then there will be resonance, and now one is known to use magnetic field, how much you have applied, and this what is the frequency, at which frequency resonance is coming. So, that is known to you. So, then you can study this effect of electron spin or effect of nuclear spin. So, this other one is NMR, okay. In that case, the same experiment, same way, externally we are using the microwave, radio wave, and magnetic field we are using. So then you will get the nuclear information, okay, of this magnetic moment of the nuclear. So, that is the spectroscopy, resonance spectroscopy, very powerful and useful, and that is why, and because resonance phenomenon and principle also very simple, okay. So, applying magnetic field and applying the radiation, in one case radio frequency, in case of NMR, and in case of ESR it is microwave frequency, okay. So, these are the two spectroscopy, very useful for studying the nuclear spin as well as the electron spin, as well as this their effect of this F, as I told, effect of the F also, this together resultant one also is using the this spectroscopy one can study, okay. So, more or less I think I complete this course, and I think this is good enough for undergraduate students. So, I will stop here. All the best for this course, and yeah. So, if you have any questions, so you can ask in forum, I will try to answer. Thank you.